Okay, so our problem is 589. The cables exert the forces shown on the pole. Assuming the pole is supported by a ball and socket joint at its base, determine the components of reaction at A. The forces of 140 kilonewtons and 75 kilonewtons lie in a horizontal plane. Okay, so we have two forces. The 75 kilonewtons of load is acting in the negative y direction at a height of 15 meters. Then we have another force which makes an angle of 30 degrees with the first one, which has the magnitude of 140 kilonewtons. Now we have a pole. There is a socket and ball bearing at A. So you can imagine that it's something like a ball encapsulated, so it can easily rotate, but it cannot go up or move in either direction. And certainly there's a cable at point D and attached to the pole at location B, and also there's another cable which is connected to the C beginning from the point B. So let's analyze the joints and isolate the joints first. So let's focus on the point B. Now, since there is a cable, this cable can only pull in the direction of the cable, and the point with the A is this. Now it's a ball joint, so it can rotate in any direction. This basically means that there cannot be any reaction moment at point A. But certainly this encapsulation avoids the translational motion in any direction. Therefore, I can easily say that point A cannot move in X direction and Y direction as well as Z direction. In fact, this results in a three-dimensional, or we will have a reaction force which has an arbitrary direction. So this reaction force at point A will have both X, Y, and Z direction, Z components. Okay, so let's draw the free body diagram of the pole. First of all, I have F1 here, and then I have F2. I just give a name. Then I have the tension in the cable TBD and tension in the cable BC. Now, I don't have any moment at point A, so I have only reaction force coming from the ground to the point A. Now let's write the position vectors. Now the origin of the coordinate is RA, so I have the components in X, Y, and Z directions are 0. Position vector is 0. RB is, so point B is located 15 meters above the XY plane, so it is 15 K vector. RC is minus 10I and plus 5J vector. RD is 5J vector. If I calculate the F1, so remember that it is 140 the magnitude and it makes an angle of 30 degrees. It is 70 I vector minus 121.244 J vector. F2 is minus 75 J vector. Now FA has all three components, FAX I vector plus FAY J vector plus FAZ K vector. Now next thing is the tension in the cables. Certainly I know that we know the directions, direction of the cables. Therefore, we can easily find the direction, but we don't know the magnitudes of the forces. So tension coming from the cables TBC is TBC multiplied by UBC. Here UBC is the unit vector along the cable from B to C. UBD is again unit vector from B to D, and TBD is the magnitude, and we don't know it. Since we know the coordinates of point B, D, and C, we can easily calculate the unit vectors. So this will be the next step. In fact, if we calculate the unit vectors along the cable BC and BD, what we are going to find is minus 0.534 I vector plus 0.267 J vector minus 0.801 K vector. UBD is 0.316 J vector minus 0.948 K vector. Now, the point is this: we have two equilibrium conditions, and the first one is sum of the forces in all directions has to be equal to 0. So this is the first equilibrium condition, which means that FA plus F1 plus F2 plus TBC plus TBD is equal to 0. Now, this gives us the following equation or expression: 70 plus FAX minus 0.534 TBC I vector plus minus 196.244 plus FAY plus 0.267 TBC plus 0.316 TBD J vector plus FAZ minus 0.801 TBC minus 0.947 TBD. So basically, this has to be equal to 0, which means that components in X, Y, and Z directions has to be equal to 0 independently. So this expression has to be equal to 0, or let me underline it, that's better maybe. So this has to be equal to 0. This has to be equal to 0. And this has to be equal to 0. Now, let's proceed. Certainly, the second equilibrium condition is sum of the moments with respect to any point has to be equal to 0. This means that array vector product FA plus RB vector product F1 plus F2 plus TBC plus TBD has to be equal to 0. The good thing with the problem is all the forces, many of the forces are located at point B on the pole, and only reaction force at the support is away from it. Certainly, array is equal to 0. If I calculate the moment with respect to point A, I can calculate the moment with respect to any point. This will vanish. This term will vanish. It's 0. And as a result, I'm left with is these two expressions. It is 2943.66 minus 4.009 TBC minus 4.743 TBD. This will be my first equation. And the second equation is 1050 minus 8.0.17 TBC. And this has to be equal to 0. Now, from the last expression, I can easily calculate the TBC. From here, I will find 130.958. By the way, this has to be kilonewtons, huh? Just corrected. Unit has to be kilonewtons. And now, after finding the TBC, I can easily find the TBD from this equation, from this one. I can find the TBD. Again, the unit is kilonewtons. So it is 509.898 kilonewtons. Now, after finding these equations, these values from the two previous ones, I can calculate the FAX, FAY, and FAZ from here. So if I substitute the value for TBC, I will find that FAX is equal to 0. Then if I substitute the TBC and TBD to here, I will find FAY is equal to 0 as well. And at last, if I substitute the TBC and TBT here, I can calculate the FAZ from this equation, from this one. So FAX is 0, FAY is equal to 0, and FAZ, we find it as 588.732 kilonewtons. So don't forget the units as I did. This is also kilonewtons, and this is kilonewtons as well. Okay,